And so anyway, what we're going to do is we're going to just kind of start off with kind of a historical perspective. And where were we 10 years ago? And probably 10 years ago, a lot of you guys might have been in grade school, right? Still trying to figure out what you wanted to do with your life, or maybe not even cared at that point. But basically 10 years ago, I was working in consulting at that time. And we had in the United States, and this was actually worldwide, we had a market collapse and a downturn in the economy. It was very, very severe. And so this happened in the fall of 2008. And so in the United States, what they had, they had a stimulus program. It was called the American Recovery and Reinvestment Act, or this is just simply abbreviated ARRA. And this started pumping money back into the economy back in 2009. And one of the portions of the ARRA was investment in utility infrastructure, or what we call smart grid. And so actually a lot of smart metering projects and a lot of distribution automation and work going on in DER, distributed energy resources, and things along those lines actually kind of see their origin as far as having a market for these devices back in the 2009, 2010 era. And a lot of projects actually related to distribution actually got off the ground in that time period as part of the stimulus program to try to get us past the 2008 collapse. So if we look about that time 10 years ago, residential PV, this is a PV you would put on top of a household, was $6 per watt DC. That's typically how we price that. And so if you multiply that by 0.8 to 0.85, that would be the AC output. Utility scale, the multi-megawatts type systems you would put out there was $3.4 per watt DC. So pretty high compared to today's prices. And when we were talking about doing things at the distribution level, like integrating renewables, we were talking about maybe 15 to 30% penetration would be possible without totally kind of redesigning our systems. Back in that time, Hawaii has always been kind of a leader in the installation of distributed energy resources like PV. They had maybe like tens of megawatts installed. And so in order to promote the growth of renewables, the Department of Energy set up a program called Sunshot. And this is kind of analogous to the United States Moonshot program, where they're trying to get people up on the moon. Well, basically what they wanted to do starting in 2011 is they wanted to lower the price of PV through investments in various types of technologies and projects. Coincidentally, that was the time that the North Carolina State University EPSI Electric Power Systems Engineering Master's Degree program got started. This was actually part of the ARRA program, because what they did for ARRA is they basically made money available to various universities to start up programs, and NC State was one that applied for it and got funding for this. And so basically about 11 years ago, the whole power program at NC State got revamped, and they created a number of different new classes that are the classes that we actually have today. And so I was basically brought on board as part of this program to kind of help get the EPSI program off the ground. So anyway, that's just some history. And I know it's a long time ago, but basically, you know, it's nice to have some historical perspective, because sometimes we don't think things are changing. You know, in the power industry, a lot of people complain, things never change. It's the same old stuff. But actually it is changing. You just have to kind of look back over the right period of time. So a lot of change in the last 10 years. So anyway, if you look at what's kind of going on now, if you look at 2021, and you know, I go and look at what's the price points for PV. You can get this as low for residential as $3.1 per watt DC, so dropping by a factor of 2. You look at utility scale, $1.2 per watt DC, you know, maybe about a factor of 3. So very rapid drop. So you can see that the Sunshot and similar programs were successful in lowering the cost. Nowadays, when you look in the press releases, what you see talk about these 100+ megawatt systems, 200, 300, 400 megawatt systems that utilities are putting in to basically replace standard generation. Now, because of the intermittent nature of photovoltaics, what we have to do is we have to firm that with battery storage, battery energy storage. So this is another thing that goes along with this. It's a complementary technology, and now we actually have people that are building these systems and building this at price points below $1 per watt DC. And what this means is we can actually get something called grid parity, where if you're just talking about energy, we can actually produce energy just as cheap with PV and battery energy storage as we can with competing sources. Now, the issue with this is, what's the intermittency? Is this firm or not? It's not always exactly firm, but it's firming up with the use of energy storage over time. We're seeing now commercial microgrids, and you guys might have heard about microgrids, and we'll talk about that later in class, that kind of helps integrate renewables with energy storage. Hawaii has well over 1,000 megawatts of PV now. In Hawaii, you've actually got circuits that are completely renewable powered right now with over 100% penetration. And what you see various utilities talk about climate plans where they're trying to go zero net carbon by 2050. Now, I'm not going to get into what zero net means, but I think what's important at this point is that, utilities are using in their long-term planning, they're actually looking at kind of like a more of a renewable based future for the bulk generation sources. But as far as the challenges, we still have a lot of issues with weather. You guys probably been reading in the news releases about wildfires in California over the last couple years. Outages associated with wildfires, it's pretty severe. Large storm damage seems to be trending upwards. So, whether this is due to climate change or not, that's another thing. But we're basically seeing that as a society, we're having to pay a lot more year after year for these climate related events like hurricanes and ice storms and things like that. And then you guys have probably seen in the news a lot of things about, like governments being hacked, a lot of cybersecurity events occurring. And this is also an issue for the power industry because we're becoming much more dependent on computer networking. And so this is kind of another cause of concern is, yeah, we get advantages from using computer networking technology, but then we also have some risks associated with that are growing as well. So this is kind of where we're at like in 2021 right now as far as power, and this relates directly to what we do at the distribution level. Now, if you guys ever want to get information for the United States about what's going on with energy, there's a government website. It's EIA, and basically what they do is they have different reports. And there's one report they have called Energy Outlook, which does a prediction of what's going to be trends like on the energy side. And if you look at electricity generation, you can see right now that we're only generating about 19% of our energy from renewables. The bulk of this is still natural gas and coal, but this is changing with time. And a lot could happen between now and 2050. I mean, this is just probably for the most part, just the projection based on what they know right now. It still shows natural gas in the future having still a significant part in the electricity energy part of supply. But of course, this could always change with time. And then when you look at what's going on as far as the mix, it shows this being heavily solar. Now, this could change if the United States decides to put a lot more emphasis on offshore wind. So anyway, these are just projections, but it shows kind of where we are right now. And these reports lag by about a year. This is why you don't see like the 2020 numbers, because the 2020 numbers don't actually become available till later on, like in 2021, right? But anyway, this is kind of where we are right now as far as these, as far as where our electricity is being generated. Why this is important to us is we're kind of seeing a trend in going from having our generation being bulk in nature at the transmission level to distributed at the local level. And so this is going to impact what we need to look at in distribution engineering. So real quick, what I want to do is I want to talk a little bit about why distribution is different than transmission and go through the syllabus. And then I'm going to talk just in kind of general what distribution systems engineering is kind of about based on this. And then we'll discuss the assignments. And for the recorded material, what I'm going to do is I'm going to record some material on distribution elements. I'm going to kind of walk you through the different distribution components and talk a little bit about smart grid. All right. So before I go on, is there any questions I can answer real quick about, you know, some of this background? You know, kind of when I talk to students about careers and what they want to do, I mean, a lot of them mention that you want to get involved in renewables and distributed generation and microgrids and distribution automation. And so anyway, this is kind of why I wanted to provide a little bit of this background, just to kind of show you that, you know, things are kind of changing in a, I guess, kind of a positive direction. Okay, so anyway, you may have seen a picture like this before, but what this is showing is kind of showing the different parts of a, I guess what I would call a power system. And we typically talk about G, generation, T, transmission, and D, distribution. So historically, all our generation were these, what we call central stations, coal, oil, but not so much oil anymore, gas, hydroelectric would be the types of sources. And when we talk about a bulk generation plant, we're talking about probably thousands of megawatts of generation at one site. We step the voltage up to lower the losses and increase our capability of sending power out to the load centers. And we have a bulk power system, a transmission line system that operates at what we call high voltages. So 765 is the highest, 138 for transmission, it would be the lowest. There are some systems, you know, like 115 kV, and there is something called sub-transmission. So it's not, you know, it's not exact where the cutoff is between transmission and distribution, but let's just suffice it to say that transmission is high voltage. Transmission is what we focus on in a class like 550, ECE 550, which Dr. Brown teaches in the fall. What I'm going to be focusing on is what happens when we have to distribute this electricity and energy to the customers. And so this would be more of a last mile system, or maybe last 5 or 10 miles, where what we're doing is we're going to step the voltage down. We'll get into these voltage levels in just a little bit. And then we supply to industrial customers, or we supply to customers at what we call the medium voltage level. And so typical voltage levels around here would be like 12.5 kV, 23 kV. Different utilities have different distribution levels. And then when we get to the customer, especially a residential customer, we step this down even further, where we have a dual 120/240 service. So if you're living in an apartment or if you're living in a house, then what you're going to have is you're going to have this dual service where the 240 is for the larger loads like air conditioning and the dryer, electric clothes dryer. The smaller loads is your conventional wall socket. So this is what you see at your house or apartment. But what we're going to be focusing on is this medium voltage part. So if I would get into this a little bit more, then here's the G level. This is 18 to 24 kilovolts at these central stations. transmissions between 138 and 765. We would have transmission substations that convert between the different high voltage levels. We have kind of a level in between called sub-transmission. Where you see sub-transmission is when you get to like a load center like Raleigh, you'll actually see a loop around the cities. And this loop is usually what's called a sub-transmission system. And then when we get closer to the customers, we have what's called a distribution substation, which steps it down to the medium voltage, where in the United States, this is typically between 2.5 and 34.5 kilovolts. And this is a line-to-line value. This is based on history. There's no US standards. It's based on history and what utilities started building probably like 100 years ago. And they've just simply kept with their voltages. And so different utilities have different voltages that they use. But at the distribution substation, when you step this between transmission and medium voltage, you have a substation, and I'll get into that in the component lecture, which I'll record in post. You also then have to regulate this voltage. And so what we do is we have these devices at the substation called voltage regulators. And what they'll do is if the transmission voltage is low, they'll step the voltage up. If it's high, they'll step it down. And basically what this does is this gives us some isolation between transmission and distribution. This is the reason why I can have a class on distribution engineering that's different than the transmission class 550. Because if we regulate the voltage at the top of all these medium voltage circuits, then what I can do is I can analyze the circuit separately, given that I'm going to keep this voltage at the top of this section fixed. And so this is a design decision that we made in order to kind of make it reasonable to control the voltage on our distribution circuits without having to worry how the voltage is varying on our transmission. So as far as the levels, bulk transmission to sub-transmission, you have a distribution substation, you have a primary feeder. And then when we get close to a customer, then what we do is we step the voltage down to the customer utilization voltage. This is simply called a distribution transformer or a customer distribution transformer. And then on the low end side, then we have what we call our services, our service feeds. Sometimes this is called a secondary, sometimes it's called service level. Mostly what we're going to be concerned about in this class is what's going on at the medium voltage level. There's not too much analysis we can do on the customer side, but most of our analysis is going to be at this medium voltage level between 2.5 and 34.5 kV. All right, so this just kind of talks about the differences between distribution and transmission, the difference between what we cover in 551 versus 550. We're talking about lower voltage levels. I put 4 in this case. There's not too many 2.5 kV circuits out there anymore. The other thing we're going to be seeing later on is these circuits are not balanced. The currents in each phase are not going to be the same once we get to the distribution level. We're going to operate these distribution circuits radially, typically. We're not going to create loops because that causes some problems with voltage control and protection. And so it's kind of like an upside down tree. You know, you have the branches going out, but then the branches don't touch. The circuits typically tend to follow roads and streets, where in transmission, they just go from point to point. They go across the fields and everything, but distribution, we follow the roads for the most part. And there's a lot of different elements. So basically, when we're modeling distribution, I mean, we're modeling all the customer connections. On a given customer, on a given feeder, there might be like thousands of elements out there. And so from a complexity standpoint, it's just a lot much more complex than transmission as far as the number of different elements. Reliability usually is more of an issue on distribution, because on distribution, you have trees growing all over the place. You have animals jumping around. Tree falls in a line, animal jumps into a line, it causes a short circuit. And so there's probably like 90, 95% of the outage events occur at this distribution level. So we'll be talking about that. And historically, there was never any generation at the distribution level. I mean, back when in the 80s and kind of like the 90s when I first started teaching this material, we didn't even worry about distributed energy resources. But now that's changing, obviously. And so now we have to spend a lot more time in the class talking about how to integrate in these distribution level sources. So I know some of you may be working in industry, and maybe you have a little bit more of a commercial power systems background, like building power systems or hospital systems, or maybe industrial systems like a refinery plant. I'm mostly going to be focusing on electric utility applications, but a lot of what I'm talking about also pertains to commercial industrial systems for distribution. So now, a lot of times when we talk about distribution, I'll have a simple diagram like this, like a one-line diagram. And basically, I'll kind of draw straight lines, left, right, up, and down, and connect stuff together because it's just easier to see it that way. It's easier to draw it that way. But the thing you got to realize is, as I said before, is the distribution system follows the streets. I mean, this is how we route our lines. And so this is actually a section of distribution feeder that feeds a lot of the apartments up and down Avon Ferry Road, which is right next to Centennial Campus. You have the substation here, and then we have a feeder coming out, and it routes down along the streets. We have these taps for getting to the apartment buildings and the houses and things like that. This is actually what a distribution circuit would physically look like. And then we'll have different components connect, like capacitor banks for power factor correction, which we'll talk about. And we have devices for protection called reclosers. But this is kind of what a distribution feeder in real life actually looks like. It's not a set of straight lines. These connections just kind of go all over the place. What we're going to worry about is what's going to happen with the voltage, because if I regulate the voltage at the substation, by the time I get down here to the end, the voltage is going to drop. And this is actually from a circuit analysis program that shows how the voltage changes from the top of the feeder down to the bottom. If the voltage gets too low, then we can't properly supply load. And so this is a big thing we're going to talk about in this class is the calculation of this voltage drop. Now, I know a lot of you are not from the United States, and I'll talk primarily in here about North American circuits. But there's different designs in different parts of the world, and if you guys are, from India or the Middle East, whatever, I'd, kind of appreciate your input on these diagrams. I can maybe add some more stuff on international circuits in here, but this is just kind of a comparison between what we see in North America and Europe, where European designs are actually probably used more worldwide. So in the United States, since we have a lot more rural customers, we typically tend to use a mix of three-phase, single-phase, and two-phase. If I have a small customer out in the middle of nowhere, I don't run three-phase, I just run single-phase. And if the more customers get added, I upgrade to two-phase, and more customers get added, I upgrade to three-phase. So there's a lot of runs of single-phase that you're going to see in these North American systems. If you talk about more of a European design, they run three-phase everywhere. And the reason they can do that is because the loads are more dense. The loads are more compacted together. And so what you'll do there, instead of running these long single-phase laterals, you'll run three-phase. And because you're running three-phase, and what you're going to want to do is you're probably going to want to connect more customers up to these distribution transformers. And so the United States, where you have a lot of single-phase transformers in European systems and other parts of the world, you'd see more three-phase transformers. So anyway, you can kind of read this on your own. I just thought this was I was using this for another presentation. I thought this was sort of interesting. And then as far as design differences, we have obviously different voltage levels that we use. And so if you're talking about more of a European style system, these distribution circuits are going to be more 11, 22, 33 kV, where what we're going to see for US are more of these levels. Excuse me for a second. Okay, so I got one question. Are cogeneration plants considered on the distribution side? And it depends on the size. If we're talking about cogeneration plants in the megawatt level, we certainly can connect these up to distribution. Maybe we can handle up maybe 5, maybe 10 megawatts. But when it gets above that level, then usually it gets kind of too large for distribution, and we have to look more at connecting maybe directly to the substation or connecting into transmission. Transmission interconnections are generally very expensive. It's very, very expensive to put in a substation just for putting in additional small generation like PV or wind power. So a lot of developers like actually trying to interconnect to the distribution level because it lowers their cost. But as we'll see later on when we do the projects, that's going to be problematic as far as these distribution systems weren't designed to handle that level of backfeed. But yeah, we'll be talking about that later on. Okay, so anyway, what we're going to be covering in here is, first of all, we're going to talk about the different elements that we see in a distribution system. So that's going to be like loads, transformers, lines, all those different types of components. We're going to be kind of going through these one by one and talking about, well, what's the model for a load? What's the model for a transformer? What's the model for a line? You've probably seen this before if you had a power systems class, but we're going to be focusing more on what the distribution type of model is. And then we're going to cover different types of analysis. And power flow is probably the most common type of analysis. Kind of similar to what you do with transmission, but you're taking into account the fact that you have single phase and two phase. We'll talk about short circuit analysis. That'll be a little bit different because of the unbalanced nature of distribution. We'll get to reliability calculations, what to expect as far as number of outages and the time duration, and power quality. Because reliability and power quality are things that are more seen because of the distribution imperfections and what happens at transmission. We'll talk about how we regulate voltage with voltage regulators and capacitors. And then we'll use tools, one from a company called Millsoft, another one from a company called EPRI, for doing analysis. And we'll talk more about these in class later on. And then also what we're spending like, gosh, about 5 lectures on is we're going to be getting into analysis of distributed energy resources like PV, what's going to be going on with like electric vehicles, and what's going to be the impact of storage and things like that. That's going to be a little bit more toward the end of the semester once we have the basics. And then we'll also talk about things related to smart grid and microgrids as well. So prerequisite for this class is you guys should ideally have a class like 451, and that's an NC State number, which is an undergraduate class on power systems. Ideally, that's what we'd like you to have. But if you've had at least a junior level class, you might be okay. Just realize that you need to be able to do single phase and three phase real and reactive power calculations. You need to be able to do phasor analysis. You should have seen transformer modeling before. You should have seen, hopefully, transmission line voltage drop calculations, use one line diagrams, some exposure to per unit. And then also it'd be good if you had seen something along the lines of a bus impedance and bus admittance matrix. Power flow analysis would be useful, as well as being able to do short circuit analysis. If you haven't seen any of this, you might want to send me a note and we can discuss, because it's going to be kind of hard to catch up because I'm not going to be reviewing all of this. Some of this I will, but not all of this. But we're kind of assuming that you probably have seen about 3/4 of this. And then when we get into the lecture material, again, we're going to be doing 2 lectures a week. And so here we are at lecture number 1. And then what I'll do next week is I'll post the material for lectures 2 and 3. So if this lecture date is listed as Monday, then what I'm going to do is I'm going to record this on Sunday and post this like the day before. If it's on Wednesday, I'll do it the day before. I'll get it posted later on Tuesday. And what I'm expecting you guys to do is to kind of keep up with this material as I post it, just like we were going to a regular class, because I'll be giving homeworks on this. And usually what I'll do is I'll do 2 lectures. And so I'll do a lecture on Monday and Wednesday. Then on Wednesday, I'll give you guys a homework assignment, which will be due the following Wednesday. And so the material, like on lectures 2 and 3, I'll give you this assignment on the 27th, and it's going to be due the 3rd. So typically you'll have a week to do the homeworks. What I'll also do too is on Monday, I'll do the kind of like the online session. And so if you have questions on this lecture, say like on the lectures on Monday and Wednesday, I'll answer them on the following Monday call, right? And then the homework will be due 2 more days on Wednesday. So that kind of gives you through the weekend at least, especially if you're working to try to catch up on the lectures from the previous week. But we'll start in on looking at loads and transformers and basics of substations and lines, etc. And then we'll get into some analysis involving how we do voltage regulation and do some basic voltage drop calculations. We'll do some of this stuff by hand, and some of this stuff we're going to be doing using computer programs. And so I still want you guys to be able to do some hand calculations so you understand it. But the reality is you have to learn how to use tools for this. And so we'll be getting into power flow analysis and show you how to do this in a tool called Windmill from MillSoft. And this is a power flow program, which they have a student version of that you can download. We'll talk about power factor capacitors and how they're applied. And that's actually 2 parts because that's kind of an involved topic. We'll get into doing short circuit analysis. And then we'll talk a little bit about protection. We cover some of this in 581, but you need the protection background to do the reliability calculations. We'll be doing a midterm exam on the 10th. That's the plan right now. This will be a take-home exam. So the way I'll do it is I'll give you guys access to the exam. You give a certain time window to work it at home. And then when you're done, you're going to turn it in. I'm not sure about the final yet, but this is going to be a take-home midterm exam. And as far as labs and books and things like that, I'll get into that in just a little bit. We're not going to be doing labs per se, but we will have projects. And so we're going to have a 3-part project. You're going to have to use power flow programs to build a circuit, to actually do some voltage drop analysis, and to do some distributed generation analysis. You don't need to buy anything for that, but I'll get to the books in just a little bit. We're also going to be talking about power quality, things like voltage sags, voltage drops, the kind of voltage drops you have when you start a large motor. There's also going to be non-60 hertz components called harmonics, which we're going to be talking about as well. And then we get into the distributed energy material. So there's going to be one day we have off because we're not doing a spring break. So they have the spring break kind of distributed. But there's going to be kind of like a DER part 1, part 2, and part 3, where I kind of talk about, well, how do we analyze DER? First looking at the circuit impact, then looking at the standards, what the standards say, and then finally how we analyze this using the computer tools. There's a second computer tool we're going to use from EPRI called OpenDSS. This is also free, and we'll get into that later in the semester. This enables you to do a more sophisticated analysis, but there's a little bit more of a learning curve to it. And then we get into some smart grid applications like automated feeders we call fault location, isolation, and service restoration. We get into advanced volt bar control. And then I'm going to have somebody from industry come in and talk about distribution design. Now, what distribution design gets into is it kind of gets into what are the required ratings on lines and transformers. So we're going to get into a little bit more depth about, well, what size transformer do we really need to keep it from overloading and burning out? And then I'll have another guest speaker come in and talk about electric vehicles and energy storage. He's been doing a lot of analysis and consulting area for this. Finally, the last lecture is going to be on microgrids. For the